Have you ever looked up in the sky during the day and been captivated by the sheer beauty of our sun? Well, if you're like me, you probably wondered where it came from. Let's take a step back on the cosmic calendar to the creation of our sun, roughly 4.5 billion years ago. Our solar system looked very different 5 billion years ago. We were in the midst of a stellar nebula. A nebula is a dense cloud of dust and gas consisting of mainly helium and hydrogen. You see, our sun was lucky in how it formed. 90% of forming stars and nebulas turn into brown dwarfs. These brown dwarfs have a very low luminosity and are not yet complete stars. When the stars were forming, not all forming stars reach a hyperstatic equilibrium, which is why most don't become successful stars. A hyperstatic equilibrium is when the mass on the inside is in an even balance with the mass on the outside, and it holds the sun together. Now you see, our sun was a medium mass star, and that's why we turned out a yellow dwarf. Now our sun is a medium mass star. What that means is our sun reached its hyperstatic equilibrium while it was at medium mass. Our sun is known as a yellow dwarf. Our sun is a very average star except with one exception. It has no partner. As far as we know, most stars live in binary pairs. This means that a star has another star and they orbit each other. Most stars you see in the sky are actually 2 to 7 stars that fit close together in a binary system. These stars are more common in our universe than single stars like our own sun. That is why our sun is very different than other stars. Now let's skip forward from 4.5 billion years in the past to 5.4 billion years in the future from present day. Our sun will run out of hydrogen. Hydrogen is like fuel for a star. When this happens, our sun will turn into a red giant. This means our sun will expand rapidly, 1.6 times bigger and 2.2 times more luminous. In 6.8 billion years from now, our sun will reach maximum red giant size and be 180 times bigger and 3,000 times more luminous. At this size, our sun cannot maintain its hyperstatic equilibrium. This is like the final stages of a top spinning. Its rotation keeping it together has become off-kilter and tumbles over. At this point, our sun goes supernova. It implodes, then explodes in a matter of seconds. We will probably be gone way before this, so no need to worry. When our star goes supernova, it ejects all the stellar materials needed to produce a new star. After a couple million years, our sun's central mass will be all that remains. At this point, however, it will be a white dwarf, a small, very dense, very bright dwarf star. After 10 to the 17th years from now, it will have cooled into a black dwarf, the final stage of our star's life. No illumination, just a dense ball of material. Now this ball is so dense with material that a teaspoon of this sun would weigh as much as our Earth. Yes, only a teaspoon of this sun would weigh as much as our Earth. Now what would happen if we were a low mass star? Well, we still would have gone supernova, but it would fuse through helium. Instead of becoming a white dwarf like our medium mass star, it would become a red dwarf, very faintly luminous and believed to be an immortal star. It would never decompose further. A perfect hydrostatic equilibrium. Now let's say we were a high mass star. We would have gone supernova too. This means much more energy is released. Because of this, high mass stars are also much denser and can create stellar nurseries, or massive nebulas, neutron stars, or it's even theorized a black hole, or a rip in space-time. We live in a fascinating and wondrous universe, and there is still much to explore.